Good afternoon, class. We are looking at Chapter 8, further applications of trigonometric functions. Here's 8.5, polar form of complex numbers, the complex plane, the Moore's theorem. So we've looked at the law of sine and cosine, polar coordinates, the equations and graphs, and now complex numbers, complex plane, the Moore's theorem. The objectives are plot points in the complex plane, convert a complex number between rectangular form and polar form, find product and quotient of complex numbers in polar form, use the Moore's theorem, find complex roots. Again, reminding everybody of basics, such as a unit circle has equation x squared plus y squared equals 1. Point P has coordinates x, comma, y, or cosine or sine. Equation of circles, x squared plus y squared equals r squared, centered at 0, 0, x minus h quantity squared plus y minus k quantity squared equals r squared, centered at h and k. Fundamental identities of such as Pythagorean identities, quotient identities, reciprocal identities, even and odd properties. A squared plus b squared equals c squared, a plus b equals 90 degrees when you're dealing with the right triangle, law of sine and cosine. Sine a over a equals sine b over b equals sine c over c. And cosine law, a squared equals b squared plus c squared minus 2bc cosine a. And you can solve for cosine a to get b squared plus c squared minus a squared over 2bc. Now, polar coordinates, reminding you that we have a rectangular coordinate system and a polar grid, and the positive x-axis of the rectangular coordinate system is the polar axis, the origin is the pole, and a point P has coordinates x, comma, y, or r, comma, theta. So in the case of a rectangular, we have x, comma, y. In the case of a polar, we have r, comma, theta. The relationship between the two is x squared plus y squared equals r squared. Tan of theta is y over x. Tan of theta is opposite over the adjacent. And you want to adjust for the quadrant. So polar to rectangular, remember x is r cosine theta, y is r sine theta. If you want to go with polar, r comma theta, you should recognize there are infinitely many ways of representing it. R and theta, also r and theta plus 2k pi, because 2 pi is a complete revolution and 2k pi, k is an integer. If you want r to be negative, you can go with negative r and odd multiples of pi. These are just rectangular and polar grids. In the case of a rectangular, it's very clear. 1, 2, 1 to the right, 2 up, negative 3, 1, negative 3 to the left, 1 up. In a case of a polar grid, we have concentric circles, and this is radius 1, radius 2, radius 3, 4, 5, and so forth. For example, if you want 2 and pi over 4, first you locate theta equals pi over 4, and you go 1, 2 tick marks. That means the second circle. 4, 5 pi over 4, you find 5 pi over 4, and you count 1, 2, 3, 4. This is how you put them, and more of them are here. Again, we have a rectangular coordinate system in conjunction with a polar grid. And this is an interesting point, reminding you that pi is on this side because this is r being negative. You go to the opposite side. So this is going to the opposite side of pi, representing minus 7 pi. And also pole has coordinates r comma theta, where r is 0. When r is 0, with any theta, we end up at the pole. As far as graphs are concerned, recall when theta is equal to alpha, that represents a line through the origin, y equals tan alpha times x, line passing through the pole, making an angle alpha with the polar axis, y equals tan alpha x, theta equals alpha. R equals A is a circle, centered at the pole, radius A, so you can see that because x squared plus y squared equals a squared. So you basically square it, r squared equals a squared, and r squared becomes x squared plus y squared. If you have r cosine theta, that can be replaced with x, and therefore it gives rise to a vertical line. So r cosine theta equals a is the same as x equals a is a vertical line. R sine theta equals a constant is y equals b, and that's a horizontal line. Now, if we have r equals 2a cosine theta or minus 2a cosine theta, or 2a sine theta or minus 2a sine theta, makes no difference. All of them represent the circle with the radius being a. It's just the location of a center that makes a difference. In the case of cosine, because cosine represents the x-axis along the x-axis. In the case of a sine, it's along the y-axis. So for example, this one gives you a comma 0. This one gives you minus a 0. Okay, and so forth. So these are some basics that I just wanted to remind you. There are more graphs that I have here, and even more here. For example, cardioids. R is a plus minus a cosine theta or sine theta. Okay, limicons and limicons with the inner loop, rows, and so on. So a sine n theta, a cosine n theta. And when n is even, the number of pedals double up. So we have different types of graphs. I just wanted to remind you, as long as you know the basics is good enough. All right. And now here's the synopsis of the section 8.5, the complex plane, the Morse theorem. Here's the summary. A complex number z equals x plus yi or a plus bi. I hope you remember that. X and y are real numbers, and I is square root of minus 1 is an imaginary number. There's really not much of brand new stuff here. Reminding you, I, by definition, is square root of negative 1. When you square it, you get negative 1 cubed, negative I, and I to the power of 4 is 1. The magnitude, also called the modulus of a z, is the distance from the origin to the point x, comma, y. Therefore, it makes it the square root of x squared plus y squared equals R, just like the R for polar coordinates. So when z is x plus yi, okay, its complex conjugate, we call it z bar, is x minus yi, okay? And this notation, which looks like an absolute value, is representing the modulus, the size, the magnitude of the z equals r equals square root of x squared, y squared is the same as z bar. I hope you know if you multiply these two, you remember a plus bi times a minus bi. It's a squared plus b squared. So when you multiply these two, you get x squared plus y squared. Okay. Okay. So X is r cosine theta, y equals r sine theta, nothing brand new. R is greater than or equal to 0, and theta is normally between 0 and 2 pi. Complex number in polar form, z equals x plus yi. And if we want to go with the polar form, we replace the x, we replace the y, we get r cosine theta plus I r sine theta. This is a shorthand notation, r cis theta. Where does that come from? This has r, so we have the r. C stands for cosine, I stands for this I here, and S stands for sine. So this is a shorthand notation. R cis theta means r cosine theta plus I r sine theta. And I hope everybody's okay with that. Here's a complex plane. We have the x and y. The x will be the real axis and the y will be the imaginary axis. Okay. This angle is theta. This is the y. And this is r, or the modulus. Z is square root of x squared plus y squared. So this is called a complex plane. So z equals r cis theta or r e to the power of I theta. I have the proof of that at the end if anybody is interested. R squared is x squared plus y squared. Tan theta is y over x. All right. What else do we want to add? Here's the summary. We will elaborate on this. The next one is when you want to multiply two complex numbers. You get R1, R2 cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Remember, so Z is R cosine theta plus I R sine theta, right? So Z1 is R1 cosine theta 1, I R1 sine theta 2, or R1 cis theta 1. So let me write that in case. So in essence, we are saying that here, Z1 is R1 cis theta 1. Say Z2 is R2 cis theta 2. That's the idea, everyone. And therefore, we have what you can see. Or Z1, Z2, as I mentioned, R1, R2 cis theta 1 plus theta 2. So what does it mean? It means if you want to multiply two complex numbers, this is the faster way. If you put it into a polar form. If you put it in a rectangular form, it becomes a little bit more difficult. Same thing with the division. Let me erase my work here. If you want to divide Z1 by Z2, you divide R1 by R2 and cosine of the sum becomes the difference. Okay. Or R1 over R2 cis theta 1 minus theta 2. De Moivre's theorem. It says if you want to raise Z to the power of n, then R, look at this one. Look at this one. R to the power of n cis n theta, or cosine of n theta plus I sine of n theta. Again, shorthand notation. Remember, cis is the shorthand notation. Now, this is interesting. If you want to find the root, if you have a number with r cis theta of sub 0 when n is larger than or equal to 2, there are n distinct complex nth root of w. In other words, you want to take a second root, square root, cube root, you name it. Then the roots would be the nth root that you want of cis theta 0 over n plus 2k pi over n, and you choose k to be 0, 1, 2, all the way to n minus 1. And of course, if it's in degrees, 360 degrees times k over n. We will look at all of these with details in a moment, everybody. All right. Let's start with the first example, writing complex numbers in polar form, reminding you C is R cis theta, shorthand notation, R squared is x squared plus y squared, tan theta is equals y over x. So plot and write complex number z equals square root of 3 minus I in polar form. So that's what we want to do. So first and foremost, here's the complex plane, and take a look at just a couple of points first. In general, this is A, this is B, so this is A plus BI, or X plus YI, or IY, however you want to call that. So for example, if I want 3 plus 2i, I go 3 to the right, 2 up, and that's my point. Just as you would do with easy pair in a rectangular coordinate. If I want minus 4 plus 3i, I go 4 to the left, 3 up. This is minus 4 plus 3i. This one is square root of 3. So I go square root of 3 to the right. Square root of 3 is about 1.7 minus I, so I go 1 down. So that's a location. Square root of 3 is about 1.73 or something like that. So they want us to plot that. We did that. Now we want to write it in polar format. We need to find r cis theta. So we need to find r. We know r squared is x squared plus y squared. So x is square root of 3 and y is negative 1. So square root of 3 squared plus negative 1 squared. They add up to 4. And therefore we get 2. So we got r. And tan of theta is y over x. And I hope you recognize y as negative 1, x as square root of 3, or minus square root of 3 over 3, and it's in quadrant 4. You remember that in quadrant 4, tangent is a negative. So let's go with the reference arc. So let's say tan theta, I'm going to call it reference arc, is positive square root of 3 over 3. So the reference arc is pi over 6. In the fourth quadrant, subtract this from 2 pi, and theta becomes 11 pi over 6. Okay, everybody? So these are cis theta. Replace the r, replace the theta. We get 2 cosine of 11 pi over 6 plus I sine of 11 pi over 6. Or you could write the shorthand notation 2 cis 11 pi over 6. Either way is fine. Okay, everybody? Plotting a point in the complex plane and converting from polar to rectangular. We want to go back and forth. So z is 2 cosine of 30 plus I sine of 30. It's very simple. Just replace the cosine of 30 with square root of 3 over 2 and sine with 1/2. As far as plotting is concerned, basically you have this rectangular grid where you have the angle 30 degrees and two tick marks along that R. So you come up with the 30 degrees and then you go two tick marks. That would be the R. R is 2. Real axis, imaginary axis. So we said this is square root of 3 over 2 with the sine of 30 is 1/2. And when you multiply by 2, the denominators, both of them go away. We get square root of 3 plus I. Very simple. So we can graph, we can convert from one format to the next. I want to write the point in rectangular form. Z equals 3 cosine of 3 pi over 2 plus I sine of 3 pi over 2. We are not graphing, we are just doing the math. We can see that R is 3, theta is 3 pi over 2 if we were to graph him. And as you know, cosine is 0, sine is -1. So this goes away 3 times negative I becomes minus 3I. So one thing you should notice, if we are dealing with pi over 2, this ends up being if this is positive number, R times I. If it's 3 pi over 2, it's R times negative I, so it becomes minus 3I. So again, if this is pi over 2, we have Ri. If it's 3 pi over 2, we have negative Ri as the answer. So that is good to remember. We discussed the product and quotient of complex numbers in polar form. If Z1 is R1 times cosine theta 1 plus I sine theta 1, and Z2 is R2 cosine theta 2 plus I sine theta 2, then Z1, Z2 is R1, R2 cosine of theta 1 plus theta 2 plus I sine of theta 1, theta 2, and Z1 over Z2 is cos R1 over R2 cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Needless to say, as always, the denominator can't be zero. I'm going to go over the proof quickly for the first one. So Z1, Z2. Let's multiply. So what happens? You're multiplying all of these. So put R1 and R2 together and then multiply these two. So put R1 and R2 next to each other. Cosine theta 1, cosine theta 2. Cosine theta 1 times I sine theta 2. So we have the I there. I sine theta 1 times cosine theta 2. I sine theta 1 times I sine theta 2. This is what we get, everybody. So one more time. These two, just this one. And you multiply these two, you get this one and you have an I. You multiply these two, you have an I. And you multiply these two, you get I squared. So notice we have R1, R2. We are going to combine these two because this becomes minus, right? I squared is minus 1. So minus sine theta 1 sine theta 2. And we combine these two and we factor the I out. So again, pay attention to the algebra behind this. This remains. We are going to put these two together as cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. And we're going to put these two together by factoring the I out. Okay, so it's very straightforward, everybody. So what do we notice? Let's look at this one. Cosine alpha cosine beta minus sine alpha sine beta. This is cosine of alpha plus beta. This is cosine of theta 1 plus cosine of theta 2. Sine alpha cosine beta plus cosine alpha sine beta. That is sine of theta 1 plus theta 2. Right? And believe it or not, this is the proof. We're done. For Z1, Z2. We proved if we're going to multiply Z1 by Z2, we multiply their R's, and then we write cosine of their sum. So in essence, a shorthand notation is R1, R2, cis theta 1 plus theta 2. Right, everybody? So that's a proof for this one. We are going to move on. All right. We proved the first one, everybody. Let's prove the second one. And the technique is to multiply by the conjugate of the denominator. So make this one minus and put it up and down here. That's the technique. So we are going to multiply this fraction, the top and the bottom, by cosine theta 2 minus I sine theta 2. We're going to multiply and divide. So what happens? I'm going to write the top, R1 times this times that, and the bottom is R2 times what? Cosine of theta 1 plus I sine theta 2, cosine of theta 2 minus I sine of theta 2. I hope you recognize this becomes, in essence, plus sine squared, or I'm going to write the bottom as a plus b, a minus b is a squared minus b squared. And I squared will be changed to -1. And this whole thing becomes plus 1. I'm not going to write the plus 1. Okay. So what is the denominator? The denominator is cosine squared of theta 2 plus sine squared of theta 2, which is 1. I'm working on the denominator. Cosine squared plus sine squared. Same argument. That gives us 1. Let's look at the top. Just distribute. Cosine theta 1, cosine theta 2. Cosine theta 1 minus I sine theta 2. That becomes minus I cosine theta 1 sine theta 2. These two plus I sine theta 1 cosine theta 2. And this last one's minus I squared sine theta 1, sine theta 2. And don't forget, this is 1. So what happens again, we're going to combine accordingly, and knowing that this, everybody, is just a plus sign because it's minus I squared, and I squared is negative 1. So we are going to combine these two. So we're going to write, we are going to write R1 over R2 times this cosine theta 1, cosine theta 2 plus sine theta 1, sine theta 2. And this part, if I take the I out, times sine theta 1, cosine theta 2 minus cosine theta 1, sine theta 2. So these two. And of course, this is what? Cosine of theta 1 minus theta 2. This is what? Sine of theta 1 minus theta 2. In other words, this is the proof. You're not responsible for the proof, but if you can follow it, you have an easy time understanding all the identities we have covered. Find product and quotient of complex numbers in polar form, where z is 3 cis 20 degrees and w is 5 6 100 degrees. We want to find z times w and z over w. So the product, we just follow the formula. ZW is R1, R2 cis. I'm going to go with the shorthand notation. Cis, theta 1 plus theta 2. Becomes crazy to write too much. So R1 is 3, R2 is 5, and then cis 20 plus 100. See how easy it becomes? So that makes it 15. That makes it cis 120 degrees. We found it in polar form and we are done. If they ask to convert it to rectangular, now we have to go with cosine of 120 and I sine of 120, and that happened to be a common arc. We can figure it out. What about z over w? R1 over R2, and that means 3 over 5 cis theta 1 minus theta 2, that means 20 minus 100. And that gives us negative 80. You can leave it like that, but if you want positive, and normally we want positive, all you have to do, add 360 degrees to that. So this is minus 80 in the fourth quadrant. You just add, because we want to go from 0 to 2 pi or 0 to 360 degrees. Just keep this and add 360 degrees to bring it to the positive complete revolution. In one revolution, the positive one, 3/5, cis 280 degrees. So that's pretty straightforward, everybody. We are going to move on. Write 2 cosine of 15 plus I sine of 15 to the power of 4 in standard form of a plus bi. Okay. There are two ways to do that. You can write this one in standard form and raise it to the power of 4, which becomes pretty difficult. But just the way it is, we raise it to the power of 4 first, and then we bring it to standard form a plus bi. They say standard form or rectangular form. Why are we doing it that way? Because now we have the advantage of using the de Moivre's theorem that says if you want to raise it to the power of n, then n happen to be 4. So z to the power of 4 is, let me just write this, z to the power of 4 is this thing to the power of 4. So 2 to the power of 4, and then 15 times 4, 15 times 4. By the way, I have the proof of that at the end by induction, because when you multiply by itself, it becomes to the power of 2, again, power of 3, and again, power of 4. And as long as a few of them work, the rest of them do work. So how do you raise this to the power of 4? You say 2 to the power of 4 cosine of 4 times 15 plus I sine of 4 times 15. That's how you do it in uh, polar form using De Moivre's theorem. So 4 times 15 makes it 60. 2 to the power of 4 makes it 16. This is 16. This is 60. And 60 happened to be a common arc. Cosine is 1/2. Sine is square root of 3/2. And when you multiply by 16, this becomes 8. This becomes 8 square root of 3i. So I hope you see that how easy we can raise this to power using De Moivre's theorem in polar form. Given z equals 1 minus I, find z to the power of 10. Well, if I want to raise z to the power of 10, 1 minus I times itself 10 times takes forever. So we're going to go with the z equals r cis theta, the polar format. So we need to find the r and theta. And to do that, remember, r squared is x squared plus y squared. Therefore, r, or modulus of z, is square root of x squared plus y squared. Please understand x is 1 and y is negative 1. And each one is 1, so we get square root of 2. So uh, in essence, r, or modulus of z, is square root of 2. Tan theta is y over x, and y is negative 1, x is 1. So tan theta is negative 1, theta becomes negative pi over 4. You can keep it with negative pi over 4. If you want to make it positive, just add 2 pi, okay? Either way is fine. We can deal with it just the way it is, because we just want to raise it to power of 10. Again, if you want to go to a positive side, you just add 2 pi to this. So just the way it is, z equals r cis theta. Therefore, z is square root of 2 cis minus pi over 4. So we want to raise this to the power of 10, everybody. Which means we're going to raise this one to the power of 10, and we want to multiply this by 10 according to this. Take a look at this one. Z to the power of n is r to the power of n, square root of 2 to the power of n. Cosine of n theta, n times this, n is 10, and this is what you end up with. So square root of 2 to the power of 10 is the same as 2 to the power of 5. I hope you know that. And this is minus 10 pi over 4, or minus 5 pi over 2. 2 to the power of 5, everybody knows, is 32. Now, minus 5 pi over 2, it's the same as minus 4 pi over 2 and minus pi over 2. You can drop that and make it minus pi over 2. So these two are the same. Or just add you can add 2 pi and another 2 pi if you want. In other words, add 4 pi. And if you add 4 pi, this becomes 3 power 2. If you want, if it's easier right now, then if you add 4 pi, makes it 3 power 2. If it's easier that way, it doesn't matter. Cosine of that is 0, okay? And sine of that is -1. So you should know that this is 0, this is -1, so it makes it -32i. -32i. And if we wanted to raise this to the power of 10, it would have taken a long time. So we say 1 minus I to the power of 10 is simply -32i. So we took it to polar form, we brought it back. And I want to write this expression in standard form. Z to the power of 6 is square root of 3 cosine of 10 degrees plus I sine of 10 degrees to the power of 6. And we are going to follow this. According to the Moore's theorem, this would be square root of 3 to the power of 6. Cosine of 6 times 10 plus I sine of 6 times 10. So 6. We're going to put 6 theta, and theta is 10 degrees. So I'm following that. In the case of n being 6, and more specifically now r and 10 degrees. So when we do that, I hope you recognize this one as 3 cubed, right? Square root of 3 to the power of 6 is the same as 3 cubed or 27. 6 times 10 is 60 degrees. And you all know cosine is 1/2. Sine is square root of 3 over 2. So we have x plus yi, or a plus bi, is 27 halves plus 27 square root of 3 over 2i. So in the form of a plus bi or x plus yi, that means the standard form of a standard form of a complex number. Find complex roots. Let W be R cosine theta sub 0 plus I sine of theta sub 0. And n is a number which is 2 or larger. N is greater than or equal to 2. And therefore it has n distinct complex roots. So each root, z sub k, so there are k roots, is the nth root of r cosine of. We are going to add 2k pi and then divided by n, or 360 times n and divide by n. And k can take all the values all the way to n minus 1. That means 0, 1, 2, and so forth. Find complex cube roots of -4. I want you to know, if we were to do this in algebra, and we have done that, we would, just to let you know, and you can finish it if you want, you would write, okay, x cubed is -4, then you bring it here, x cubed plus 4 equal to 0, and you try to factor this. Okay, it could happen, and then you come up with three answers. One answer is real and two are imaginary. So let's look at the methodology that we use here, which is a lot easier than that. So let me erase this. Just, and again, this may be, difficult to grasp, but what if they said, okay, cube roots of 1, you would say x cubed equals 1, x cubed minus 1 equal to 0, and you would factor this. Okay? And just to remind you, a cubed minus b cubed is a minus b times a squared plus ab plus b squared. And please understand, this one doesn't have 2, it's not a perfect square, and when it's plus, this becomes minus. Okay, just to remind you how it can be done possibly in algebra. Okay, now we want cube root of 4, and we are going negative 4, and we are going to, let me erase this. We are going to rewrite number negative 4 in the form of r cis theta. And some of you may recognize that when the angle is 0 degrees, you really get a positive here, and when it's pi, you get negative. So minus 4 is 4 cis pi. Please understand, r must be positive. So 4 cis pi or 180 degrees. You can use either one. I'm going to discuss it both ways ultimately, but let's go with degrees. It's a tad easier. And n equals 3 because we want the cube root. So minus 4 is 4 cis pi. You can expand it and see that. Let me just show you why you should know that. So 4 cosine pi plus I sine pi. As you know, this goes to 0, right? Because sine pi is 0. And cosine pi goes to -1, so you get -4. So if you have a positive number, let's say 4, then it will be 4 cis 0. If you have negative, you have 4 cis pi. If you have 10, is a 10 cis 0. If you have minus 10, it's 10 cis pi. Just to give you an idea. All right, now that we have the format that we want, we are going to go with this. And we want z sub k. We want the nth root of r, which is the third root of 4. Remember, n is 3. Cosine of, this is theta sub 0. So you see, this is r. This is theta sub 0. So theta sub 0 is 180 divided by n, which is 3. 2k pi. Since I'm going to go with the degrees, I'm going to put 360 degrees k divided by 3, and the same thing goes here. So take a look at what we put here. You can do that, or you can write, if you want to go with pi here, then this is 2 pi k, okay, everybody? Either way works, but it might be a tad easier to work with degrees. So let's see what happens. I'm going to erase my work and continue with this. So cube root of 4, cosine of 180 over 3, plus 360k over 3. Same thing here, but I sine. So 180 over 3 becomes, this becomes 60. This becomes 120k. And the same thing happens here, okay? And k is all the numbers all the way to n minus 1. K must be 0, 1, 2. Stop. If you go to 3, you get this back. Class, if you go with 3 times 120 is 360. So it goes a complete revolution and comes back to 60. That's why you stop. All right. So now, if I put k equals 0, class, if I put 0, I get 60. So cube root of 4, cosine 60, I sine 60. If I put 1, I put 1. If I put 1, I get 120 and 60, 180. If I put 2, I get 240 and 60, 300. So put 0, 1, 2. Here's what you get, everybody. Cube root of 4, that doesn't change. Cosine of 60 plus I sine of 60. Cube root of 4, cosine of 180 plus I, or just cube root of 4 cis 180. Cube root of 4 cis 300, whatever is easier. So what do we notice? Let me again erase my board. The modulus of 0, r, is square root of x squared plus y squared. All cube roots have magnitude cube root of 4. The arguments are 60 degrees, 180 degrees, and 300 degrees, the arguments. Equally spaced at 360 degrees divided by 3. So that means, remember, this is 0 degrees. So it starts with 60 and then 120 and 120. So all 3 points are equally spaced on a circle. X squared plus y squared equals cube root of 4 quantity squared. This is the circle, everybody. It's important to understand what's happening here. So look at the circle. So how do you locate them? Here's the circle centered at 0, 0. The radius is cube root of 4. The radius is cube root of 4. The first one is 60 degrees, so this is 60 degrees, everybody. This is 180 degrees, this is 180 degrees. In other words, since there are 3 of them, 360 divided by 3, each one must be separated by 120 degrees. So take a look at this one. Complex cube root of 1. Remember, it's 1 cis 0. I mentioned that positive number versus negative number, right? 4 cis pi. This is 1 cis 0. Starts with 0 because it's cube root. 360 degree divided by 3 is 120. So it's 120, 240, and so forth. You can go through the process and see that in this case would be 1 cis 0, 1 cis 120, 1 cis 240. So those are the 3 roots of number 1. It'd be fascinating if you check it out, class. All right. Plot 3 minus 4i in the complex plane and write it in polar form and write theta in degrees. Normally, they tell you how they want it, okay? So in degrees or otherwise, okay? So 3 to the right, 4 down, z equals 3 minus 4i. This is the angle. So tan of theta is negative 4/3 because it's y over x. Y is negative 4, x is 3. And this you have to use a calculator, tan inverse of negative 4/3. Okay, gives you negative 53.13. If you want to go with the positive theta, then you have to subtract it from 360. This is just to calculate the theta. Okay. R is x squared plus y squared under the radical. This is r squared. And we get 9 here, 16 here. They add up to 25. Comes out as 5. So r is 5. And z is x plus yi or r cis theta. So 3 minus 4i is r, which is 5 cis 306.87. Okay. Now, again, we are using positive. You should always represent it with positive. When you do the calculation and they want you to, for example, go from this format to this format, if you have a negative number and you want to continue, that's fine. But when you're representing it in this format, you have to go with from 0 to pi to 2 pi or 0 to 360 degrees. Example 10, use the Morse theorem. Write 2 plus 2i to the power of 6 in standard form, a plus bi. And again, we don't want to raise this to the power of 6. We are going to change it to r cis theta, the polar form. To do that, we need to find the r. And first and foremost, we can see that x is 2, y is 2. So r is the square root of x squared, which is 2 squared, plus y squared, which is also 2 squared. 4 and 4 gives us 8. And square root of 8 is 2 square root of 2. Remember, this is 2 to the right, 2 up. In the first quadrant, tan inverse of 2 over 2, which makes it tan inverse of 1, which is pi over 4. So 2 plus 2i is r cis theta, 2 square root of 2, cis pi over 4. So this could be written as a cis pi over 4. Okay, that's the same. Now, we want to raise this to the power of 6. So we are going to raise, according to this, we're going to raise this one to the power of 6, and we're going to multiply the angle, the arc, by 6. So let's see what happens here first. This is 2 to the power of 6. times square root of 2 to the power of 6 is 2 cubed. 2 to the power of 6 is 64. 2 cubed is 8. Their product is 512. This one is 6 pi over 4 or 3 pi over 2. As you know, cosine of 3 pi over 2 is 0. Sine is -1. So we have 512 times -1i or minus 512i. If these three cis 130 or cosine 130 plus I sine 130 and W is 4 cis 270, 4 cosine of 270 plus I 270, what is the product? ZW. Well, we're going to go with the product rule. Z1, Z2 is R1, R2, cis theta 1 plus theta 2. Therefore, this would be R1, R2, cis theta 1 plus theta 2. So we are going to plug in R1 is 3, R2 is 4, theta 1 is 130, theta 2 is 270. So 3 times 4, cis 130 plus 270, or cosine of 130 plus 270 plus I sine of 130 plus 270. So they add up to 400 degrees. 3 times 4 is 12. We want to bring it to the first revolution. So we want to go from 0 to 360. Therefore, we are going to subtract 360 degrees, results in 40. So 12 cosine 40 plus I sine 40, or simply, or 12 cis 40 degrees. And again, notice 40 and 400 degrees are coterminous. Want to find complex roots? Find the complex cube root of -1 plus square root of 3i. Leave the answer in polar form, use degrees. All right, so we are going to go to R cis theta. That means we need R, which is the square root of x squared plus y squared. X is -1, y is square root of 3. This gives us 1, this gives us 3. They add up to 4, and therefore the square root is 2. Now theta is tan inverse of y over x, tan inverse of square root of 3 over negative 1. And by the way, this one is uh, x is negative, takes us to the, and y is positive, takes us to the second quadrant. So tan inverse of square root of 3 over negative 1. So this is tan inverse of minus square root of 3. Remember, for square root of 3 would be positive 60 degrees. For negative would be negative 60 degrees. And we want to go to quadrant 2. So we are going to add 180. So class, the inverse will result in this answer. Because we wanted in quadrant 2, we are going to add pi for 180. So the answer is 120. So pay attention to why it goes from negative 60 to 120. Therefore, we are going to write the number negative 1 plus square root of 3i is 2 cis 120 degrees, or cosine 120 plus I sine of 120. And we are interested in the cube root, okay? So z sub k is the nth root, the third root of r, which is 2 cis theta 0 over n. Theta 0 is 120 over n is 3 plus 2k pi over n plus 2 plus 360k divided by 3, because you can go with that or the degrees. In this case, they're asking for degrees. So one more time, cube root of r, which is 2, and then you put theta 0 over n, and then add 2k pi or 360k divided by 3. So when we divide by 3, we get 40 here, we get 120k, and k can go from 0 to all the way to n minus 1, 0, 1, 2, and it stops. Because again, if you use 3, 3 times 120 makes it 360. So z sub 0, if I plug in this one with 0, this goes away, I get just 40 degrees. Cube root of 2, cis 40 degrees. If I replace this with 1, I get 120, and 40, I get cube root of 2, cis 160 degrees. If I go with 2, 2 times 120, 240, and 40 is 280. I get cube root of 2, cis 280. So we are done, but I want to show you what happens as far as the graph is concerned. So we have a circle with r being a cube root of 2. Therefore, x squared plus y squared is cube root of 2 quantity squared. That's the circle. And the first one starts at 40 degrees. The next one at 160. The next one is at 280. And the difference is that 120 degrees that we had r cis 40 plus 120k, everybody, right? This was plus 120k, remember that. So it just adds 120. So looks like all 3 points are equally spaced on a circle of x squared plus y squared equals cube root of 2 to the second power. Okay, looking like that. So x squared plus y squared is cube root of 2 to the second power. 40 degrees, 60 degrees, 280 degrees. So this one, again, I'm rewriting it. The first one is at 40 degrees. The second one is at 160. And the last one is at 280. And the difference, the angle between them, this is 120, 120, 120. In other words, 360 degrees divided by 3. The reason it's divided by 3 because you want the cube root. So 120 degrees would be the difference between them.